And you guys, I know that you above all are extremely busy people. I realize that. I realize you can't do everything, but this is not a huge commitment for time, and I think you'd enjoy it. So, all right, let's check it out. Okay, so what we've looked at so far, everybody, is we've looked at this. We've looked at the derivative at a given point. Okay, and so derivative means what? Do you remember what it means? Slope, instantaneous rate of change at a given point. Instantaneous, slope at one point, instantaneous rate of change, not average rate of change, not secant lines, tangent lines, and that's what makes it so special. We're going to teach you how to do this really quick in a few days here, but at a given point, we said that f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. What you want to learn today, and so some people are going to say, well, isn't this what we already did? Well, kind of, but we just want to state it differently. And this is what we refer to as the formal definition of the derivative, okay? Formal definition is this. F prime of x. Now, instead of saying a specific point, we could say that the derivative can be written as a function so that you can put in just about any number and get out just about any result. And so this is the most formal way of writing it. We say that that is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So the only change is that we've replaced the variable a with x. And the only reason we do that is we say that the derivative can be written as, again, a function where, it changes values over a given domain. So this is an operator. The derivative, is an operator. And when I say operator, I mean that we do things to operate mathematically. Can you name some of the most basic operations that we do in math? Addition, subtraction, division, multiplication. There's other things we do like powers, right? Like we might square something. I'll give you some other operators. Natural log of something. Another operator. Sine of something. Cotangent of something. Have a blast. I'll even give you a different one. F inverse. Do you remember from pre-calculus what it means when we do F inverse? Exactly. You switch the x and the y values. That's what we did. And you can even do this. Do you remember what this does? If we have sine inverse, do you remember what that does? Not 1 over sine. That's the way you get the angle. So you have a decimal and you do sine inverse to then get the angle. Okay? Well, other operators that imply derivative. This is the one that we are going to use most often. F prime of x. Okay? That is the one we will use most often. There's all sorts of different operators, and when you get to college, your professor might use some different ones. And depending on the notation that we're using and the formulas we're trying to work with, we might use some of these this year as well. Another one would be y prime. Not too different there, is it? You might see d over dx. That's very common. That also means that you're taking a derivative. You might see dy over dx. You might also see, I had to look in a book to find some of the others. So it tells you how much they actually use them. You might see that. Or that. Or that. These first four are the most common. Okay, so now I need what you're learning right now. You're not going to directly apply today, but it is so important for when we do something called implicit differentiation. We are going to engage all the time right now in what we call explicit differentiation. Explicit differentiation is where you have a variable that's solved for. So I want you to think about this for a second. Okay? You have a line. What is the slope of that line? 3. So what is going to be the instantaneous rate of change of that line at any given point? 3. So would you agree that if I take the derivative of this, I would get 3? Now that was an easy one to do. We can all look at a line and see that. It's different when we get other stuff. But watch this. When I actually take the derivative, I work on both sides. What is the derivative of y? What do you think? Y prime. Now, Emma, did you say 1? That is correct, except it's 1y prime. And we'll get to more of that later, okay? Equals, and you said that the derivative of 3x plus 2 was 3. So you actually operate on both sides. And when I say you operate, you're actually doing this thing right here. That's what we're doing. Okay? Now let's just switch it and get back to what Emma said earlier, because she made a very good point. What if I have 2y equals 6x plus 4? Would everybody agree that that's exactly the same as the previous equation that I have? It's just different by a factor of 2, and multiplying through by a factor does not change the way the equation looks or the way it has solutions. So, do you know what the derivative of 2y is? It is 2y prime. And what would the derivative be of 6x plus 4? What would be the slope all the time of 6x plus 4? 6. So notice if we solve for y prime, we get y prime is equal to 3. Now, you don't necessarily know right now why the derivative of 2y is 2y prime. We'll talk about that when we get to what we call, again, implicit differentiation. But right now, we're always going to have a variable solved for. I just want you to understand that we are operating on both sides. Are we all good there? Okay. So I drilled that through your head. Let's move on. Use the graph of, I'm sorry that this didn't turn out very well. I don't have any of my files to print today. I had to make copies. For some reason, I came back to school, and everything that I have on the server is gone. So I should say that I cannot access the server, so hopefully that'll change. I put in a complaint, too. All right. Use the graph of f of x to the right to the left. So here's what we want to do. If we could graph the original function, we should be able to graph the derivative if the derivative is also a function. Now, without actually taking an equation and mapping it out, let's look at this graph and be able to find some values. Specifically, I'd like to look at -4, -3, -2, -1, 0, 1, 2, 3, and 4. And what I'm going to do is, looking at those x values, I'm going to try to estimate what f prime is. Okay? Now, estimate f prime is simply the slope of the tangent line at a given point. Now, here's something that you all should come to understand right now, is there are spots that I should look for to do first. What are the best spots to be able to find the derivative of right away on that graph? Where it's 0. So, again, we're going to approximate this because the graph isn't perfect, but for approximately what x value does this graph have a slope of 0? Everybody agree that at -3, f prime is approximately 0? And Larry said at 0. I would agree that at 0, it appears to also have a slope of 0. True or false? A graph will always have a derivative of 0 at 0. No, we could definitely give you another graph that didn't have it. You know, if you graphed a line, it wouldn't have a slope of 0, 0. So there's all sorts of possibilities. And then 2 also has 0. So how would I show that on the graph to the right? Yeah, exactly. That's where it crosses the x-axis. So I have negative 3, 0, I have 0, 0, and I have 2, 0. Now, I'm going to do two other things, okay? 0 is where you change from what to what? Positive to negative or negative to positive. So, if I go to this side of 0, is the slope positive or negative? Negative, so I'm just going to put negative. How about between the next two zeros? Positive. And how about between the next two zeros? Negative. And how about between the next? Positive. So you can see that I'm going to have those kind of values. What does that mean in terms of my graph? Negative, positive, negative, positive. Where is it going to be in relation to the x-axis? Negative will be below and positive will be above. So we'll actually generate some estimating values right now, but just note that you'll be below the x-axis, above, below, above. Okay? So let's get some estimated values here. We have negative 4. So at negative 4, 1, 2, 3, 4. So I have this line, so I'm just going to draw it. And I'm going to estimate it, okay? If I go over 1, I go down, what would you say? 1, 2, 3, 4, 5. Say 5? Negative 5? Okay, so I think negative 5 would be or negative 6, somewhere around there would be a realistic value. So I'm finding the slope at that point. We know the slope at negative 3. Now let's look at the slope at negative 2. Again, I'm going to draw a tangent line. So it looks like if I go over 1, I go up what? 2. I would say that, would you agree, a slope of 2 is a good approximate value? Okay, let's try negative 1. If I do negative 1, I could go over 1 and up maybe about 2, maybe a little bit less. We'll put 1.5. We know it's less. It's tough to draw really good tangent lines, isn't it? Yeah. How about at 1? What does the slope look like there? I go over 1 and about down 1. Would you agree it's about negative 1? And if I try to find f prime of 3, oh boy. Oh, that looks pretty steep, doesn't it? Over 1 and up, yeah, maybe like 5. And then 4 might be even greater, say 7, something like that. I would have a tough time even trying to draw that. So now if I simply plot these values, negative 4, negative 5, negative 3, 0 we have, negative 2, 2, negative 1, and 1.5, or negative 2, somewhere around there. 0, 0 we've got. 1, negative 1, I can draw that. 2, 0 we've got. 3, 5, 3, 5, 4, 7, something like that. Whatever. What kind of shape do you get? Cubic. Who recognizes the degree of the graph that we had when we started out? Not quadratic, it was quartic. Quartic, you can tell from this quartic. Notice that when I mentioned this before, when you take a derivative, the power decreases by 1, and that happens all the time. Okay? And so, do you feel like you could look at a graph and make an estimation? Again, we started by finding where the slope was 0, and then we moved from there. We confirm positive, negative, as it looks right there, and we're good to go. Okay? All right. So, we like to take derivatives, but there's this key. In order for a function to be differentiable at point A, this must be true. These two things. Okay? F of x must be continuous at x equals a. If you're going to take the derivative at a, it better be continuous. Would you agree? If you want to have an instantaneous rate of change, there better be something there to find the instantaneous rate of change of, right? Second thing, and this is not notation that your book uses, so don't ever show your professor, but this is the best way that I can write it for you guys to understand. So the second requirement is this. F prime of x from the negative must be the same as f prime of x from the positive. So the rate of change from the left must be the same as the rate of change from the right. There's fancier ways of writing that, but I think that that's the best way for us to understand. So let's look at 3 examples where it's not differentiable. This is a function right here. Basically, all polynomials are differentiable everywhere. They're great to work with. So like this guy, differentiable everywhere. It's continuous everywhere. We like to use it. But here's an example where you are not differentiable. Not differentiable at x equals negative 3. Anybody want to guess why? Well, it has what we call a corner. And so here's what we could say. If you take the derivative of the function from the left, what's the derivative at negative 3 from the left? What's the slope from the left? It's negative. Negative something, maybe negative 1, who knows? What if I take the derivative of it from the right at negative 3? It's positive. So you can tell that they're obviously not the same. So therefore, you cannot find a derivative at negative 3. Some people want to say it's 0. Like, well, yeah, you just average the two out and you would get a 0. No, it does not work like that. It does not work like that. Get rid of that. Ugly. Dick. All right. Here's another one. This is discontinuous at x equals 0. Who knows why? Discontinuous. Remember, if we got to pick up our pencil to draw it, it's not continuous. Now, if you looked at the left from the right, you might say, well, from the left it looks like 0, from the right it looks like 0. That doesn't matter. It's not continuous. And the last one's a tricky one. Okay? This is the one that messes people up on the test. Good. So, first of all, it's discontinued. This one is not differentiable at 2 spots. Number 1 at x equals negative 3, and second of all at x is equal to 0. And here's the reason why. Emma had the first one. You said it's not a what? Yeah, it's not even a function to begin with. Because it fails the vertical line test. Okay? That's at x equals negative 3. But look at it, x equals 0. This is an interesting one. And this is kind of difficult, okay? If you were to draw a tangent line right at 0, what would that tangent line look like? Straight up and down. If you have what we call a vertical tangent, what's the slope of a vertical tangent? We don't know. It's undefined. And so what you have here is a vertical tangent. How about this? We only have 2 problems on the back side to do. Let's do those tomorrow, and you'll have the rest of the hour to work. Okay, let's do that. Finish up your assignment from last week, people. So then tomorrow we could engage in this one. You'll have time to work. Join math team.